Ever opened a physics textbook, looked at a problem, and just felt that wave of intimidation? Yeah, we've all been there. Well, you're in the right place. Today, we're going to take one of those classic, tough-looking problems and crack it wide open, step by step. The goal here is to turn that confusion into aha moments. All right, let's dive right in. Here's the beast we're tackling today. Problem 1.131 from IA Irodov's Problems in General Physics. Now, if you know the name Irodov, you know his problems have a reputation for being, well, pretty gnarly. But don't you worry, that's exactly why we picked this one. If you can understand how to solve this, you'll master some core concepts that show up everywhere in physics. So, here's our game plan. First, we're going to talk about the big idea, the link between energy and force. Then, we'll use that to find the stable equilibrium point. After that, we'll hunt down the point of maximum attraction. And finally, we'll put it all together and actually visualize what's going on. A nice logical path from start to finish.
Before we even think about touching the math, we got to get the big picture. And the relationship between potential energy and force, it's one of the most powerful ideas in all of physics. And the best way to understand it is with a really simple analogy. First up, potential energy, RU. I want you to completely forget the scary equation for a second. Instead, just picture a landscape. With hills and valleys and flat plains. The potential energy of a particle is nothing more than its altitude, its height, at any given spot on that map. That's it. Okay, so if energy is the height, then what's the force? Well, the force a particle feels is just the steepness of that landscape. It's the slope. Think about it. If you're on a really steep hill, you feel a strong pull downwards, right? That's a strong force. If you're on a perfectly flat piece of ground, there's no slope, so you feel zero force pushing you either way. And here's the math that brings our analogy to life. Force is the negative derivative of potential energy. For this problem, since everything just depends on the distance r, it simplifies to F equals negative du by dr. Now that minus sign, it's not just there for decoration. It's absolutely crucial. It tells us that the force always points downhill. It always pushes a particle towards a place with lower potential energy. All right, let's put this idea to work. Part A of the problem asks us to find the equilibrium position. So using our landscape analogy, we're basically looking for a very specific spot on our map. So what exactly is equilibrium? Well, physically, it's any point where the total force on our particle is zero. And what does that mean on our energy landscape? It means we're looking for a perfectly flat spot. A place where the slope is zero. A particle could sit there all day and not feel a push in any direction. So how do we find that flat spot with math? We just follow these steps. We start with our potential energy function U. Next, to find the force, we take the negative derivative. Now be careful with your signs here. This is a super common trip-up. The derivative of a over r squared is negative 2a over r cubed. So the negative derivative is positive 2a over r cubed. Get it? Then we set our whole expression for force equal to 0. A little bit of algebra later, and boom, we find our equilibrium position. R0 is at 2a over b. But hang on a second, finding a flat spot isn't the whole story. We need to know if it's a stable flat spot. I mean, is our particle sitting safely at the bottom of a valley, or is it balanced precariously on the very peak of a hill? If it's in a valley, a little nudge will just make it roll back down. That's stable. If it's on a hilltop, the tiniest puff of wind sends it rolling away forever. That's unstable. So, how can we tell the difference mathematically? We have to look at the curvature of our landscape. And the tool for that is the second derivative of the potential energy. If the second derivative is positive, it means the curve is shaped like a smiley face. It's a valley, a minimum. And that tells us our equilibrium is stable. Okay, let's run the test. We need that second derivative. So we take the derivative of our first derivative. That gives us 6a over r to the fourth minus 2b over r cubed. Now, we don't care about the curvature everywhere, just at our equilibrium spot. So we plug in our value for r0, 2a over b. I know the algebra looks a bit hairy, but when the dust settles, it simplifies down to b to the fourth over 8a cubed. And since the problem told us from the start that a and b are positive, this whole thing has to be positive. A positive curvature means we're in a valley. Our equilibrium is stable. Check. All right, on to the second part of the problem. Now we're asked to find the maximum attraction force. Now listen up, because this is a totally different question, and it's a really common place for people to get mixed up. We are not looking for where the force is zero anymore. Think about our landscape. We're now trying to find the spot with the absolute steepest downhill slope,
We're looking for the maximum value of the force function itself. It's a classic optimization problem, just like you did in your first calculus class.
And how do you find the maximum of any function? You take its derivative and set it to 0. So, we're going to use the exact same strategy as before, but this time we're applying it to the force function. We take our expression for f, we find its derivative with respect to r, and then we set that new expression to 0. Solving that equation for r gives us the location of the maximum force, which turns out to be r equals 3a over b.
Okay, so that's where the force is strongest. But the question asks for the value of that force. No problem. We just take our location, r equals 3a over b, and plug it right back into our original equation for the force. It's just a bit of algebra, and what pops out is our final answer. The maximum attractive force has a magnitude of b cubed over 27a squared.
Okay, we've crunched a lot of numbers and done a bunch of calculus. Now for the really cool part, the payoff. Let's actually graph these functions and see what this all looks like. This is where the math turns into a clear physical story. So here it is, the graph of our potential energy landscape. Look at that. When r is really small, that a over r squared term takes over, and the energy shoots up like a giant repulsive wall. Then the graph dips down into this little valley, what physicists call a potential well. And guess where the absolute bottom of that well is? Exactly where we calculated at r0 equals 2a over b, our stable equilibrium point. And now for the magic. Watch how the force plot perfectly tells the story of the energy plot's slope. Where the energy shoots up, the force is huge and positive. That's repulsion. As the energy curve slopes down into the valley, the force becomes negative. That's attraction, hitting its peak right where we found it at r equals 3a over b. And then, at the very bottom of the energy well, where the landscape is flat, the force crosses the axis. It's exactly 0. It all fits together perfectly. So let's just boil it all down. The strategy is always the same. Force is the negative slope of potential energy. Equilibrium is where that slope is 0. Stability is all about the curvature, the second derivative. And finding the maximum force? That's a whole separate step, where you find the peak of the force curve itself. That's your toolkit. And to finish up, let's zoom out for a second. Why should we care about this specific function? Well, it turns out that this shape, with a strong repulsion at short distances and a weaker attraction at long distances, is an amazing model for how two atoms interact in a molecule. So the math we just did isn't just for a textbook problem. It's the fundamental physics that explains how molecules, and pretty much everything around you, are held together. Kind of cool, right?